Now we'll try an example. If you look at this problem, what's the atmospheric pressure if the partial pressures of nitrogen, oxygen, and argon are those three numbers respectively? Well, this sounds like Dalton's law of partial pressures. Your total pressure is the sum of all your individual samples. So I need the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon equaling the total. Well, I don't know the total, but I do know the nitrogen is 745 millimeters of mercury. I know the oxygen is 22 millimeters of mercury. And I know the argon is 3.6 millimeters of mercury. If we add them up, the total pressure of the whole sample of gases would be 770.6 millimeters of mercury. Remember, when you add, the rule for significant digits is to round to the least precise measurement. This was to the tenths, that's the tenths, that's the tenths. So my answer needs to be to the tenths place. The second one is also a Dalton's law problem, except in this case they give me what the total pressure is. The atmospheric pressure is this, and it's made up of nitrogen and oxygen, and I just want to find the oxygen. Well, P total equals the pressure of the nitrogen plus the pressure of the oxygen. The question says, what is the pressure of oxygen in millimeters of mercury? Which is fine, but then I need every pressure in millimeters of mercury. They give me the nitrogen as 760 millimeters of mercury. I don't know the pressure of oxygen, but my total pressure, my atmospheric pressure, was given in terms of ATMs, or atmospheres. So I first need to convert that. 1.03 ATMs. I know 1 atmosphere of pressure is the same thing as 760 millimeters of mercury. When I convert and multiply those, you get 782.8 millimeters of mercury for the atmospheric pressure. I can plug that in over here, 782.8 millimeters of mercury. And then to find the pressure of the oxygen, simply subtract 760 millimeters of mercury from both sides, and we're left with the pressure of the oxygen equaling 22.8 millimeters of mercury.